So far, actually, we have learned the concept of static electric charges, okay, and related phenomena. Now, today, we'll be learning uh, when the charges are not stationary, when they move. So we'll see in this chapter, we'll be dealing with the motion of the charges, and the motion of the charges gives current, and since this current we are getting due to the motion of the electric charges, so this current is called uh, electric current, okay, current electricity, current due to electricity. So see, current actually a very normal, a very general word, current. If I give you that a simple example, then you might be able to appreciate. So today we'll be learning current electricity. So as I said, current means, current is actually a very general word. This can be applicable for anything. We can say air current, okay, air current. We can say water current. You might be heard of water current, okay. So these are very normal. See, this current is actually a general word, which means actually flow, flow of some things. In this case, air current means flow of air. Okay. Here, water current means flow of water. Okay, flow of water. So here, current electricity means flow of charges. Flow of charges. So the first and second chapter we have dealt with static charges. Okay, static charges. In the first chapter we have learned electric charges and fields, and second chapter we had learned potential, right? Potential and capacitors and all. Okay, so even though in the capacitor there was flow of charges while charging discharging, but still that phenomena is actually coming under almost in the static part. So today we'll be dealing with the motion of the charges, which actually sets a current. Current means flow of charges. Okay, flow of charges. How do you, or I can say current means rate of flow of charges. Rate of flow of charges. Flow of charges. So quantitatively, actually, it is denoted by I. Sometimes people write even small I also, depending on the situation, small I, capital I. So this is current denoted by. So current is denoted by I. Okay. And how do you define? Okay, we'll come to the definition part. So when uh, we will define the current, let us actually think of a conductor. Okay, let us think of a conductor in cylindrical shape, or maybe I'll just take this is suppose a water pipe. I'll just give you an in general idea of what is current. So suppose this is a water tube. If I take a cross section normal to the flow, so flow of water is like this. Okay, flow of water is like this. So if I take a cross-sectional area, suppose A, okay, area, cross-sectional area, perpendicular to the flow, direction of flow, perpendicular to the direction of the flow, then the net amount, okay, sorry, net amount of water flowing across this is actually called flowing across. So net amount flowing across this area, which is perpendicular to the flow of the water, is called current, and the rate of it actually called, if suppose there is a delta W amount of water is flowing in time delta T, flowing across this in delta T time. So I can write water current. Suppose IW I write. So water current is this. Okay, this is how I can define. Similarly, we'll be taking this cylindrical symmetry in our case of conductors also. Okay, when we talk about electric current, we'll see the flow of charges. So in that case, flow of charges, how do we define current in that case? We'll take up a cylindrical conductor and take a cross-sectional area perpendicular to the flow, perpendicular to the direction of the electric field. Okay, electric field. Okay, so before I go to the definition of the current, okay, current, I'll just tell you one more thing. See, when I have a conductor means what? They have free electrons. It seems. So what does that mean? So conductors have free electrons. What do you mean by free electron? What do you mean by free electron? Actually, if you have a single atom, you have a nucleus, okay, where the whole mass is concentrated and it has positive charge, and same amount of negative charge will be, and negative charges, namely the electrons, will be flowing, revolving around it, right? And the electron in the outermost orbit will be loosely bound. Okay, loosely bound. Suppose this one. Okay, this electron will be loosely bound. Loosely bound. But still, it will be under the action. See, under the attraction of, or within the attraction electrostatic force of this nucleus. Okay, it will not leave. Simply, it cannot leave the atom. So it will be together with this nucleus and the other electrons as well. So, but this is called actually valence electron, which is loosely bound. So I can actually treat an atom. How I can treat an atom? I can treat an atom as a positive core. This is core of the atom, and the valence electron kind of this. Okay, valence electron. I can treat this actually. Okay, this is a positive ion core and one electron. I can treat a complete atom in this way. Okay, on an average, these electrons may be very loosely bound, but it will not leave the atom as well, at the same time. But when, see, in the conductor, when, see, conductor means it is a solid material. Suppose I take a piece of iron or a the cylindrical shape of iron bar. So it does not have only one atom, right? It does not only contain one atom. In fact, it has almost of the order of 10 to the power 23 atoms actually. Okay, Avogadro number, almost of the order of Avogadro number. Suppose I have a piece of iron like this, so I have closely spaced atoms like this. Okay, and I said individual atom can be thought of ion core, positive ion core, and one valence electron out of, like, in the outer orbit, valence electron. But when they are individually situated or isolated atom, this is the situation. But when they are coming closer, like all the atoms are coming closer to each other, then what happens? the electrons outside, because of their orbital overlap, these electrons will be almost free to move from one atom to another and through the whole solid material. Okay, so electrons on a single atom will not be situated just there on that single atom. Rather, it can move when all this. Actually, there is again many good physics inside it. That is very conceptual physics. So there is actually a common potential. Okay, so they will create a common potential under which all the electrons, say electrons from this guy, electron from this guy, electron from this guy, all of them will be almost free to move anywhere in this solid. Okay, anywhere in this solid. Okay, but when we don't have any electric field across this, okay, across this material, what will happen due to thermal motion? Due to thermal motion is equivalent to, if you might have learned in your uh, 11th standard thermodynamics part, thermal energy is equivalent to average kinetic energy. Okay, thermal energy is equivalent to average kinetic energy. So what will happen due to thermal energy or thermal motion? Electrons will be actually randomly moving inside the solid. How they will move? One electron start from here, it will be moving randomly like this. Okay, they don't have any net direction of the velocity. Net direction of the velocity, they don't have any net direction. No net direction of the velocity of the electron. So if you take the average of the velocity of each electron, suppose vi, so what will happen? Because it is changing its direction, because the motion is random and it is changing its direction each and every moment. If you take the time average, okay, or summation, okay, I'll take time average, not summation, time average of this velocity of individual electron. So this will come out to be 0. Okay, why? Because it is, see, sometimes it is this way, sometimes it is this way, sometimes it is this way. So if you take all around, so the velocity everywhere the same, every direction is same. Okay, okay, so in this case, so what happens when they are actually randomly moving in a solid? What happens? There are ion cores are there, positive ion cores. Okay, so they will collide with each of them or among them also. Electron can collide with electrons also. Okay, electrons also. They will collide among themselves or with the ion. This is how actually their motion will be random and their directions will be like the direction of the, and see, there is a concept called able to hear me? I don't know why many people are leaving and then arriving again and again. Is there any problem with the network or something? Okay, so are you people able to hear me uninterruptedly? Someone has to respond. Nikhil, Priyadarshini.
Yes, sir.
Okay, good. So if you remember in elastic collision, what happens if you have a massive body or very heavy body with initial velocity 0? If electron is very light, it has velocity this. So what will happen after collision? What will happen? This electron will go like after the collision, the electron will have the same velocity but with negative sign. Okay, with a negative sign. That means it will not lose its velocity in the elastic collision. collision. Okay, after each collision it will have the velocity the same, but the direction will be random. So because of that, I don't have any clear cut direction of or net direction of velocity of electrons. Okay, I don't have this. So because of that, we don't get net current. No net current we get. Okay, no net current. Current means flow of electrons. Okay, flow of charges. In case of actually you have, see, if you go for, you will discuss here, if you have electrolytic cell, you might have learned in your chemistry also. So electrolytic cell, in electrolytic cell both positive and negative charges move. Okay, both of them move. Okay, both move. Okay, but in case of solid conductor, only what we take is moving is actually electron only will be moving, and the positive ion cores are very heavy, so they will not move, they will be stationary. Okay, this is the situation for conductors, and this is what actually free electron means. Free electron means what? Now, in the conductor, the electrons can move randomly inside the conductor. So that is called free electron. Free electron doesn't mean that it will come out of the metal surface. Okay, it will not come out of the metal surface unless you shine light or if you give enough heat or uh, like electric field. So this will be learning in the modern physics. This is called photoelectric effect. When we shine with photon, then the loosely bound or free electrons will be coming out of the metal surface. So that is photoelectric effect that we'll see later in the modern physics. So what I was trying to define is actually what is current. So current, look here, what happens. So if I take a cross section area A, suppose net charge delta Q is flowing normal to this, the normal to the direction of this cross sectional area in time delta T. Then how do I define current? Current will be delta Q by delta T. Actually, this is rate of flow of charges. The rate of flow of electric charges. Okay, I'm taking the modulus of the electric charge. Okay, so that's why this current generally will be writing as positive. In fact, we will see the current is flowing in this direction, like in the opposite direction of the electron flow. Okay, so if the electrons are flowing in this direction, leftwards, my current will be flowing in this direction, rightwards. Okay, my current will be flowing in the rightward direction. Okay, so yeah, so this is the definition, and further we can actually define the definition. Uh, yeah, so rate of flow of electric charge. So this again, we actually, if I correctly define, you have to take a limit. Okay, limit delta t tending to 0, delta q by delta t, and according to calculus, you can write even this as dq by dt sometime. Okay, so this is the current. Okay, this is electric current. That is nothing but rate of flow of electric charge. Electric charge. Okay, so now let us see in your book. We'll just follow the textbook chronologically. So we have defined what is current. You can see from here. Okay, so this is the definition, and it has unit ampere. Okay, it has SI unit ampere, and see, current has a direction, but it is not a vector quantity. It is a scalar quantity. Okay, it has a direction, but it is not a vector quantity. It is a scalar quantity. So in our very many natural phenomena, current is actually charges, huge amount of charge flow. Suppose in case of lightning. So in case of lightning, yeah. So in case of lightning, what happens? The huge amount of current flows uh, from the cloud, actually from the cloud to the earth. Okay, through the atmosphere. Okay, so now as I was discussing what is conductors and what are the free electrons. I have already told this thing. Now we'll see, we'll try to understand what is okay. So one more thing actually. So there are two things actually. There are two types of current. One is actually instantaneous current, and another one is actually called uh, steady current. Okay, so instantaneous current and steady current. What is steady current? Steady current means continuous flow. Okay, steady current. There is steady current. That means steady current means constant current. Okay, constant current. And there is instantaneous current also. Instantaneous current, actually see, so instantaneous current may be like this. Suppose this is the current, this is the time, so it will increase and again decrease, something like that. Okay, so this kind of current also there, but in, so this kind of current we don't actually use in our practical purpose. We see whatever appliances we have in our day-to-day life, whatever appliances we use, like electric bulb and fans and etc. So all these equipments, those are actually run by this steady current. Okay, steady current. So to get a steady current, what do you need? You need external source, external source, external source. Okay, we'll let you know how external source can give you steady current. Okay, so suppose there is a conductor. Okay, there is a conductor. Okay, so conductor means what? They have free charges, free electrons, but the net flow is zero. Net flow is zero. Okay, so this is the condition of a conductor. You will not get a current. Do you get a shock when you just simply hold a bare wire? You may not. Okay, so if that is not connected to some power source, you will not get like shock if you hold any conducting wire or something like that. Okay, so there is no net flow for a conductor, simply a conductor. But if you give an electric field, if you give an electric field, then electrons will be actually having a definite direction or net direction. Then the current will flow. Actually, if your electric field direction is this, then what will happen? The okay, let us see. I'll just uh, take up one simple example as given in your book. Let us take this conductor, cylindrical conductor, and these flat surfaces are actually these flat surfaces are, so there are supposed two discs, okay, having positive, one having positive charge. This is a dielectric disc. It can have only one type of charge, excess charge, and another disc, suppose it has only negative charges. These are actually dielectric disc, okay, dielectric material disc, and these are bound charges, so they, okay, so they cannot flow. Okay, so what will happen? So this, suppose this is with a negative charge. Okay, this is also a dielectric material. So I just put this here one side, okay, and another disc in this side. So you look here, there is actually, whenever we have learned actually in the first chapter, whenever there is a charge separation kind of this, so there will be electric field developed, and electric field direction will be from positive to negative. Okay, this is the direction of electric field. If there are two different like positive and negative charges, okay, even a single charge also can create an electric field. So this is this direction, okay, and in case of negative, the electric field will be inward. Okay, so that we have learned. So when I have a positive and negative charge together by like with the separation, so in this case, look, we'll have electric field in the direction from left to right. Okay, now what will happen when there is an electric field developed? Say I know electric field will give a force on the charge, that is Q into E. So conductors, in this actually you have a core and electrons. Okay, so core positive cores are not mobile. What are mobile is actually this the electrons. These electrons are mobile. What will happen? So the electrons will be accelerated. See, since electrons have negative charges, the force will be actually just opposite to the direction of the electric field. So electrons will actually move in this direction. Okay, electrons will move in this direction, and as soon as they reach over here, see the positive charges are there already, and when one electron comes here, what will happen? This electron and positive charge, they will make each other neutral. So similarly, another electron will come and make neutral, another electron will come make neutral. So after some time you look what will happen. So this will be simply a cylindrical conductor like this with no charge, no electric field, no current. So as long as these charges are getting neutralized, you will get current. So that current actually is called steady current. Okay, that is called steady current as long as this positive and negative charges on like over the either surface are not getting neutralized. Till then you will get a current, constant current, that is called steady current. So constant current means steady current. So in this case we have seen these are the dielectric dishes. Okay, these are two dishes. So when they are getting neutralized, there is no electric field. Electric field will be zero. But if there is any process in which I can give a constant electric field across this conductor, what will happen? You will get a current which will be steadily flowing for like infinite time. Okay, as long as you want, you can keep the electric field across this, and you can get the current that is actually the steady current. So yeah, so this steady current, what is steady current, and all those things we'll be discussing in later in this chapter itself. But first, what we'll learn the Ohm's law. You might have already learned. So this part we have discussed now. You just read this part and then see whether you can understand. If you don't understand, you can ask me anytime. So this Ohm's law we'll be discussing now. Look, what does Ohm's law said? Actually, it was 1828 when uh, G.S. Ohm had discovered this phenomena of like. So what is the physical phenomena or mechanism? It is related to flow of currents. Okay, flow of currents. So there are various materials. If you if you develop same amount of potential difference or electric field across uh, the conductors, all will not give rise to the same current. Okay, but what is the reason for that? Reason is actually the property of each material, and that property which actually resist or restrict the flow of current is resistance. So what Ohm actually discovered is that uh, the current I, suppose, see there. Okay, I'll just go to my presentation. So suppose I have, oh sorry, I have a piece of conductor here having length L, suppose, and the potential difference across this is V. Okay, now we are learning Ohm's law. So what Ohm actually discovered is, and suppose the current flowing through this is I. So he had seen that the V is proportional to I. Okay. If you increase the potential difference, current also will increase. Okay. If you decrease the potential difference, current flow will be decreasing. So he has seen that the potential drop across or potential difference across this is proportional to the current or vice versa. Okay. So if we want to make an equation out of it, so I can write this is V is equal to IR. So this is the proportionality constant, and this is called resistance. You might have learned already this thing in your previous classes also. So it is just a repetition. V is equal to IR, and it has a unit ohm. Okay, and this ohm, okay, this is denoted by just a minute. Okay, so this denoted by actually denoted by this. Okay, this is a symbol. This is ohm. Okay, this is ohm. Okay, so we have learned this. Now what else? Oh, he had again discovered that if you have another identical, suppose there are two conductors of length L and same dimension, all other dimensions are same, and connected, they connected in series, kind of this. See, then what he had seen actually, the current, sorry, the potential will be okay, so it was actually V is equal to IR. Just a minute. So V is equal to IR. This is actually Ohm's law. Okay, this is Ohm's law. Today, what we'll learn, this Ohm's law will learn in another form. Okay, this is Ohm's law. Ohm's law, but this Ohm's law will learn in another form. Okay, so this resistance actually depends on various factors. Okay, various factors. So first, this resistance actually vary with this, like this. R is proportional to L. Okay, yeah, okay, so this can be proved very well. See, if I take two identical uh, conductors of the same length, and they have same potential difference V and V. Okay, to do that, look, now their potential difference is 2V, but the same current is flowing through that. So what we got, resistance is equal to V by I. V by I. Okay. So for this case, see, I have potential difference total across this is actually 2V, but current what is flowing is same current, because when we connect them in series, they will be actually the same current will flow. Okay, whatever current is starting from here, or whatever charge is flowing through this conductor, the same charge will flow through this conductor also. Okay, that's why from the conservation of charge we can say that the current in the series actually will be the same for both. So I can get the resistance in this case. See, I have 2V potential by R. So what I get is the V by I is equal to R. So you get R. So when you have the length 2L, you get resistance how much? 2R. So what we can say from here? We can say that the resistance is actually proportional to the length. That means if you increase the length of the conductor, you'll get more resistance. Okay, this is proportional to R. So this is one. We have got another uh, rule also, or another dependence. Let's see, if so resistance actually depends on material and its dimension, its length, etc. So which we are going to now see that we have already seen that resistance is proportional to L. Now we'll try to understand how resistance is proportional to 1 by area. Okay, this will try to understand. Suppose I have the same conductor, length L, the potential is V. Okay, potential is V across this. Okay, now if I just divide into two parts like this, okay, divide into two parts like this, the same current, see, you have at the same potential, same uh, length, everything same. What is different actually? See, if I yeah, so what is this actually? This is a by 2, this is a by 2 area. Now if I had the area, total area A, now area had been divided into 2. So look, the potential actually, not the potential, I should say the current actually had been divided by 2. Okay, current had been divided by 2 in both cases. Okay, current had been divided by 2. So if I try to write the current, see, you'll get a resistance. So you'll get I by 2, so V by I is equal to R. So you'll get 2R. See, you'll get 2R. What does it mean? When you are just making the area half, you are getting double of the resistance. Okay, that means what? The resistance actually is inversely proportional to the area of the conductor. Okay, so look, if we put together all these proportionalities, if I just put together all these proportionalities, then what we get is uh, what we will get is this L by A, or in terms of equation we will get rho L by A. What is this rho? This is called resistivity, which is actually the right resistivity. Okay, resistivity. This is a material property. Material property. This is material property. That means what? It will be different for different material. If you take iron, if you take copper, if you take another uh, like conductors, it will vary material to material. Okay, so this is how we have seen that this is rho L by A. Okay, so now see, this is actually the dependence of resistance on this. So look in your book, these are the things they have discussed. Then we'll actually derive a nice form of Ohm's law, which is a different form. See, this was, now if I write potential, if I now write, so I have got, suppose I'll just go to the next slide. So with the same conductor, suppose I have length L, area A, length L, in the this potential V, and now have got what is R? R is rho L by A. Okay, so the same current I is flowing through this. So what I can write as potential is actually potential difference across this conductor IR is equal to IR. Look, this I can write, instead of writing R, I'll write in this rho L by A. Okay, so this term I by A, this you have already learned in the previous chapter. Like see, in case of Q by A, what we say? Surface charge density, right? Surface charge density. We denote it by sigma, right? So similarly, in case of current also, current per unit area called actually surface current density or current density. Current density. Current density. How do we define? How do we write that? Current density we write either small j, or sometimes people write capital J also. We denote it by J. And what is the, this is, what is the unit? The unit actually is ampere per meter square. Ampere per meter square. So this is the unit for current density. So look, I can write this as J rho L. I can write this. Okay. Now suppose I told that electric field across this. So what will be the electric field across this? Or in other way, if I know the electric field across, like through this electric field is E, then what is the potential in terms of, like what is the potential difference in terms of electric field? I can write, in the previous chapter we have learned already. Uh, there is a relationship between the electric field and the potential, that is equal to minus dVdr, okay, dVdr, or if I take the modulus, then I can write the V is equal to E into R, E or E dr I can write, okay, E into R I can write. So in this case I can write V is equal to E into L. I hope you agree with this, okay. So what I can write is this, I can write E into L, I can write this, okay. This was the electric potential difference across this conductor. So I write E is equal to E into L is equal to V. So I can write from here to this. Okay, I have got, what I have got is this E into L, and in the right hand side I have got J rho L. Now look, uh, see, I can write this I can strike out LL, and see what I can write is this. Uh, See, I can write J current density is equal to E by rho. Okay, this I can write from here. I can just keep these are vector quantity also. This current density is a vector quantity. Okay, so current is not a vector quantity. Okay, current is a scalar quantity, whereas J, okay, this is a vector quantity. Vector quantity.
Sir, current is
You know.
hello. Sir,
Yes. Yes.
sir,
Yes.
sir, how current is scalar? Sir,
I.
it's not scalar.
What is that?
Sir, current is not a scalar quantity.
What is that quantity then?
Sir, it's not scalar and not vector. Intermediate something it is called.
Okay. Yeah. You are correct. Actually, you are correct. Yeah, you are actually correct. But in general, we'll talk about scalar only. Okay. In general, we say scalar. So it is neither. Yeah, you are right. You're right. But in general, we say scalar. Okay. In general, we say scalar because we don't think like
Because
see,
it
it has
does
a
not
direction.
obey that
Obviously, it is a
addition, sir.
vector addition or the scalar addition. Scalar addition. Yes. You are right.
Yes.
In one sense, you are right. Yeah, this is yes. Okay. Yeah, this is yeah, that is correct. But in general, we say scalar. Okay, in general, we say scalar.
Sir, thank you.
Okay. Yeah, in general, we say scalar. Okay. So so then how come, you might be a question like having a question, then how come this J is a vector quantity? Why it is a vector quantity? Because we are defining the current as this J is actually I by A. Okay, I by A. That means what? Actually, this is the area. Okay, so the current this current density has a direction perpendicular to A. Okay, along the direction of unit normal. Okay, unit normal to the area. That's why this is a vector quantity. Okay, this current, see, not because of this current. Okay, because of this area has a direction. Okay, because of that this is a vector quantity. So yeah, so you can see we have got yeah, so this one by rho also has, like we can define one another single term, 1 by rho. So that is actually sigma. So this sigma is not the sigma charge density. These are not equal. So this is called conductivity. Okay, this is called conductivity. Conductivity. This is called conductivity. Okay, this is called conductivity. So I can write this as, so I can write J is equal to sigma into E. So this is actually the other form of Ohm's law. This is Ohm's law in another form. You have already learned. You have learned V is equal to IR. That is one form, but this is another form of Ohm's law. Okay, Ohm's law. J is equal to sigma into E. Okay, this is another forms of Ohm's law. So yeah, so far you have any, if you have any doubt, people can ask, or otherwise I'll go to the next topic, next part of it. Anyone has any problem or any doubts? Nikhil, do you have any doubt?
Sir,
Or yeah, yes, yeah,
Sir.
Kirtana, tell me.
sir,
Yeah.
as resistivity is depends upon material, does conductivity also depends upon material?
Yes. Exactly. Because they are just reciprocal of each other. They are just reciprocal of each other, so they both depends on the material. Okay, they both depends on the material. And you see, we'll be learning in the 15th chapter. 15th chapter, there are materials called conductor, semiconductor, and then insulators. These are the materials
Semiconductors.
like definitions of.
Infin-
Yes. So depending on the value of this conductivity or resistivity, we'll be defining the material. Okay.
Okay.
Yeah, these are actually, yes, they depends on material to material. Okay, different for different material. Okay. Somya, so I think Nikhil had written that he doesn't have any doubt. Okay. Okay, I hope everyone has understood this. Or if you have any questions so far, if people can ask, like Kirtana is asking questions and clarifying things. Okay, if people can also ask such questions. Okay, so I'll just go to the next topic. Uh, Next section we'll be learning. This is again interesting. Uh, okay, so drift of electrons. Okay, and the origin of resistivity. So this part, because we are already 6:50, already 6:50, 54. So what I'll do, I'll not write too much here. I'll try to brief out the concept over here, and then wherever required, I'll try. Okay, in my presentation. So first of all, we have to learn what is drift of electrons, and what is the origin of resistivity. So resistivity we have learned, okay, or the resistance we have learned, but what is the origin of the resistivity? I have already partly discussed that. That I have already told you that the electrons, free electrons, while moving due to thermal motion or anything, due to even if you give the electric field, then also while moving or during their motion, they will be suffering collisions, multiple collisions. Okay, to go from one conductor like one end to another end of the conductor, they will be colliding several times. Okay, so see, as I said in the beginning, that if we don't have any electric field across the conductor, what will happen? Due to the collision, you will not get any net direction of the electrons motion, no net direction of the velocity. So their average velocity, look here, it is written. So the average velocity will be 0 due to their random motion. Okay, due to their random motion. Now suppose okay, so how do we write that? See, suppose the vi, see there are, suppose I have taken a conductor, suppose. Okay, I think I better will be I'll write. Okay, so maybe I may go up to 7:10 or 7:10 or something. Okay, of the class. If you don't mind, please stay back. Or if you have another class, may leave. We can repeat some of the portions if you have not listened. Okay. So what we have seen in a conductor. So when electron moves, so there are actually, see, positive ions, they are sitting over there all around. Okay, and see, there are not only one electron. I said 10 to the power 23. Okay, of the order of this, maybe much more than that. Okay, so you have all like many electrons. So when you don't have any electric field, so sorry, no electric field, then what happens? There is no net direction. So suppose I have n number of electrons, n electrons, n number of electrons. Okay, and if I suppose ith electron having a velocity vi, having velocity vi. So what will happen for that? See, it will see, suppose there is iron core over here, 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 all around. So what it will do? It will just collide this, then it will collide this, collide that, like that. It will collide with everyone. Okay, and finally, what you will see, the velocity is so random that to take the average, sorry, average of that velocity, or the sum of the velocity, even you can say the sum of the velocity over a time interval t. Okay, you get 0, because see, we have to treat it as a vector, and when we see random means what, you will actually have in all directions equal velocity with so, so this way, and this way, and this way. So all direction you have the uh, like velocity of the electrons. Okay, because the motion is random. So this v will cancel each other, this v and this v will also cancel each other. So one point you have to note that the collisions are see, collisions are actually elastic collisions. Okay, that's why, see, before collision it was having velocity v, just after the collision also you'll have the same velocity v. Okay, but with a different direction. This is due to the massive ion, like due to the elastic collision with electrons and the massive ion, positive ion. Okay, so because of that there will be no current. Now look, if I have a electric field across this, so what will happen? Electric field, what they do, actually they gives a force. That means you have an acceleration for the electron. Now you have acceleration for the electron, so I'll write E, and then m E, this is the mass of the electron. So you'll have a, because the electric field is constant, so you'll have a constant acceleration on them. Okay, now I'll try to find out the situation, like say what is the velocity of ith electron. Okay, during during time interval t, during time interval t. And suppose, see, I have multiple collisions like this, like this. Okay, suppose just uh, t times, see, just before the time t interval t, it has a collision, one collision. Suppose I have a collision over here. Okay, and just before it go for the second collision. Okay, I mean to say in between, consecutive collision, consecutive collision, I'm seeing the time interval. So that is suppose ti. Okay, this is the time ti. Ti time it elapsed just before the second collision or consecutive collision, consecutive two like consecutive collisions. This is the time it spent, and during that time, it will actually move with a uh, uniform velocity. In fact, with an uniform velocity, and it will maintain a straight line. Okay, it will go in a straight line. So between two consecutive collisions. So this happens, and this velocity actually, okay. So this velocity, see, they move with an average velocity. Actually, this is called drift velocity. So between two consecutive collisions, because of this applied electric field, the electrons will move with an average velocity. Okay, okay, with an average velocity. That velocity is called drift velocity and denoted by v drift. Okay, that is called drift velocity. So one interesting thing is, see, when there is an electric field, the electrons actually experience an constant, like a constant acceleration, but still the electrons will not have accelerated motion. It will have a constant, like a uniform, like motion with an average velocity. So that is drift velocity. Okay. So we have to derive the expression for the drift velocity, and then we have to derive expression for j, like how we can derive with this j and other parameters. So which, okay, let us now see the situations during time interval t. Okay. Now suppose my ith electron has velocity vi when just after one collision, and suppose ti time it takes just before the second or the next collision. Okay, before next collision. This is the time before next collision. So we can find out, see, this ti may not be the same interval for all the electrons. It may vary. So when I take the average of this time, I can denote this average time as tau. What is so this time is called relaxation time. This tau is actually called relaxation time. Relaxation. Why relaxation? Because this is the time it takes before consecutive to collision. This is the time, average time between two consecutive collision. Okay. So this time is called relaxation time. Okay, relaxation time, tau. Okay, so now see, if I just think of a single electron and single collision, like just after the collision and just before the consecutive collision. So during that time, what happens? The electrons will be having an acceleration a. So what will be the velocity during this ti time? This is the time ti, right, for a single collision. I'm not taking the average now. So I take the average later. So what will be the velocity for that? So I'm taking only one electron, but there will be nth electron. Okay. So the velocity will be, see, okay, I'll just denote this by capital V as like just to keep the consistency with your book. Vi. Okay. This is the velocity during this ti time. What is that velocity? See, you have suppose initial velocity vi, and what do you know? The acceleration is this a into ti, right? So this is for uniform, like acceleration. This is one of the uh, kinematic equation, right? Now I'll write this is vi. This is the velocity during this time. Okay, during ti time, and see the a. Okay, so a I'll be writing this by m. M is the velocity of sorry, mass of the electron. So this is again, so this is t. Okay. So now if I take the average of this, what I get, if I take the time average of this, what I get is this. See, this average. So this is a constant term. Electric field is constant. Only thing is, sorry, this is ti. So I'll take the average of this. Okay, this was average is tau, not the sum set, the average. So this we have denoted by relaxation time tau. See, this will be zero as I said, because this is the instantaneous velocity just after collision, and this velocity is random velocity. This will be zero. If you don't understand, you can ask me again. So, and this I'll write Vd. This is V drip. So what I get, this is actually V drip I'm writing. Okay, average velocity of that. And this is actually E into E by m, and this average is what? This is tau, right? So this is the velocity. Look, what does this mean if I write in terms of vector? So the velocity of the electron will be opposite to the direction of the electric field. Okay. So this part, have you understood? If you understand this part, all other portions will be very much easy. Okay. Other portions will be very much easy. I think Kirtana has already left. Nikhil has already left. Only I think Mridula and Priyadarshini is there. So okay, okay. So again, yeah, Somya is there. Today Somya is not asking any questions anyway. So I think I'll then stop it because these students have left. With this, I'll stop today. So up to drift velocity, how do we get this expression for the drift velocity? You just read up to this portion. Okay, this is important. The rest of the part we'll do in the next class. So now, please up to this, you just read and see. There are many concepts till now whatever I have taught. You just read and try to understand. If you have any doubt, again you can ask me on the next class. And further we'll be extending our discussion on this part again. Okay. So okay, with this we'll stop today's class. Next class on the Sunday we'll be discussing, like we'll resume this discussion. We'll try to establish a relationship between the drift velocity and then conductivity and all other terms. These are very important terms. There will be another term called mobility and all those things we'll be learning again. Okay, so I think we'll stop it here today. If you have any doubt or question, you can ask me another 2 minutes, or otherwise I'll stop it here. So Somya, you don't have any doubts today? Do you understand everything?
Yeah, sir, I understood. I'm clear now.
Okay. Yeah. What about Mridula? You also understood everything? Okay. I hope you understand. If you don't understand, then you can ask me on the next class. Today I'll stop it here. Okay. Okay, then bye.